Section 14.4 has three topics basically. We have trees, spanning trees, and Kruskal's algorithm. Trees, spanning trees, and Kruskal's algorithm. So last time I talked about trees and spanning trees, just really briefly. What are they? I'll just pull up the problems that we looked at last time. A tree would be a graph where all the vertices are connected with edges, but there are no circuits. So basically a tree is connected and there are no circuits. So this number 4, that one is a tree. Number 5, not a tree because there's a circuit. And then something that might be disconnected would not be a tree. A spanning tree is a tree. It's a subgraph of another graph. The other graph is likely not a tree in the work that we're doing. But it's a tree. It connects all the original, the vertices of the original graph. So it's connected. The original graph would have been connected. The spanning tree can only use edges that are on the original graph. So here's a problem that I drew previously. Here's a graph, and I drew all 3 spanning trees at the bottom of the page there. So I just use enough edges to get all the vertices connected. No circuits. One fact about trees is that the number of vertices you have, for example, this bottom graph, that's a tree, 1, 2, 3, 4, 5, 6 vertices, there will be 6 edges. The last topic is Kruskal's algorithm. And Kruskal's algorithm is a method to find a minimum cost spanning tree of a graph that you're given. I'll go ahead and write that. Kruskal's algorithm is a method to find a, or the word the might fit. I'll put a/the minimum cost spanning tree of a graph. And I put a/the. Sometimes there might only be one answer. Sometimes there's more than one correct answer. But the answers you get will be the minimum cost. It's not like when we did Hamilton circuits and we did nearest neighbor, you had to, with nearest neighbor, you got a route that was a good cost, but it wasn't guaranteed to be the minimum cost. In this situation, we get the minimum cost. I'm going to draw a graph. I'll show you how Kruskal's algorithm works. See, in my head, I'm thinking maybe something rectangular shaped or slightly rectangular shaped. It's a bit slanted there. I'll put this little circuit there. Let's put an edge going out right there. So there's my graph. Let me label the vertices A, B, C, D, E, F, G. And I'm just going to make up numbers to put next to the edges. So C to G is 5, D to E is 4, F to G, we'll make that one 3, B to D is 10, A to B is 3, A to E 4, E to D is 6, and we'll do E to F is 9, B to C, let's go 6 for that. All right, so there's a graph. What you do for Kruskal's algorithm is you list the edges in order from lowest to highest. So, now I said edges, but list the numbers, list the weights in order, lowest to highest. So you really don't need to write what edge it is. We can see that from the graph. I'll usually circle them on the graph when I have them in my list, because if I don't, I'm liable to skip something. I see 3 and 3. There are 2 4s. 5, 6, oh, there's another 6, and then 9 and 10. Then you start selecting from the smallest ones. Your edges you select do not have to connect as you go, but they're going to connect when you're done. So I look at A to B is 3. We'll take that one. Let me mark it here that we used a 3. There's another 3, F to G. We'll take that one. Then I move on to the 4. You select it if it does not complete a circuit. A to E would not complete circuits with what I've already selected. D to G would not complete a circuit. Then I have 5. I'll take that one. So far, I have not completed any circuits. And now I get to 6. 6 would connect these 2 parts, and either 6 would do the job. Do you see that? I could take either one. Do I want to take both of them? No, because that would create a circuit. If I take E to D, then I have this nice looking spanning tree. If I took this last 6, that would make a circuit. So don't take this one. I'm going to mark through it with an ink pen. 9, no. 10, no. Now this problem I wrote sort of just happened that I had to select all the smallest ones. That's not always going to be the case. To find the cost, you add up the ones you selected. 3 plus 3 plus 4 plus 4 plus 5 plus 6. So that's 14, 19, I get 25.